Good morning, everyone. It's wonderful to see so many familiar faces, especially in person. Since the workshop focuses on information acquisition, and the first task usually is elicitation. So I'm going to talk about elicitation. And I titled the talk Context-Aware Elicitation, mainly because I want to emphasize that elicitation actually requires some knowledge. So we actually have to first have some knowledge about the setting that we intend to acquire information for before we can achieve successful elicitation. And the talk is based on joint work with Feng from Harvard and Fang-Yi from George Mason University. Both of them are here, and they will be able to answer any questions that I cannot handle. So let me just briefly talk about my plan. So I want to first spend some time to emphasize that elicitation requires knowledge. So please excuse me that I'm going to just go over some very basic setups of the elicitation problem and some of the classical mechanisms that's successful at achieving truthful elicitation. And see what type of knowledge those mechanisms leverage on in eliciting the underlying information. And this is trying to really argue that since we need knowledge in order for us to achieve successful elicitation, we should really think about that any elicitation is situated within the context of the elicitation tasks. And we can leverage our knowledge about the context to achieve successful elicitation. Once we start to think about that, we will be able to achieve elicitation for settings that we were not able to achieve before. In particular, I will talk about how we can achieve elicitation for pairwise comparison data and also data over social networks or opinions over social networks. And we want to emphasize that we really prefer a simple mechanism. So our starting point is that if we start with a simple mechanism, can we identify the knowledge that's necessary for a particular elicitation task such that the knowledge plus the simple mechanism will allow us to design something that can achieve successful elicitation. So let me just dive in. To give you a very basic setup of what do I mean by elicitation. So elicitation usually is referring to that there is some random variable. So this can be the random event that we're interested in getting information about. And this random variable probably follows some prior distribution. And at this moment, we're not assuming any knowledge about the prior distribution. And then a realization of the random variable is like realized, it happened. So it's a draw from the distribution, but we don't know the realization. And if we're thinking about an agent may have some private information about this random event, about the random realization of the X, we usually think about that the agent has some private information S. So S is a random variable, but the random variable is correlated with the event X according to a joint distribution Q. And after X is realized, the agent also receives the realization of the signal S. So the S is the private information that we're interested in eliciting. So the very basic elicitation question is that, can we incentivize the agent to truthfully report the realized signal S? Is there any guarantee that we can get? So without any knowledge, we're thinking about that, we know nothing about what I just described. So we don't know the prior distribution, we don't know P, we don't know Q, we don't know the realized X, and S is the private information of the agent. So I think you all agree that it's impossible to guarantee anything if the principal has no knowledge at all. So after all, even the Archimedes requires a place to stand to move the Earth. So we definitely need something to be able to achieve successful elicitation. But then let's just go over some very basic mechanisms to say, for successful elicitation, what type of knowledge that people have leveraged in those mechanisms. So the first very well-known one is that suppose X is the weather outcome. So we're forecasting tomorrow's weather. And then the principal will observe the realized weather outcome X in the future. So if the principal will be able to observe the ground truth X, then this is a very simple elicitation question. And it is well known that the proper scoring rules incentivize the agents to truthfully report his prediction about the random variable X. And the proper scoring rule incentivizes that because according to the agent's true belief, reporting that true belief maximizes the agent's expected score. And this is really the easy elicitation setting. And the community has really divided the elicitation problem according to whether the principal has access to the ground truth, which we do have a place to stand, to leverage, and to incentivize the agents to report their information truthfully, versus when the principal doesn't have access to the ground truth. So when the principal doesn't have access to the realization of the X, even in the future, we usually call this is the setting called information elicitation without verification or without access to the ground truth. And that's considered to be a much harder problem, but many mechanisms, collectively called the pure prediction mechanism, have achieved the truthful elicitation at equilibrium. But they all leverage on some knowledge. So let's just gradually take a look at what type of the knowledge that they've been leveraging on. So this is a case that the principal doesn't have access to the realization X. So all the principal has access to is what the agents reported. So in this case, a single agent is not enough because the principal needs to have some additional knowledge. So suppose that the principal can ask two agents to answer the same question or complete the same task, and also assume that the principal knows the distribution queue. And this allows the very original pure prediction mechanism to work. So essentially, it turns the elicitation problem into a problem of predicting another agent's signal. So essentially, if agent one, who's Alice here, truthfully report his signal as A, the principal will be able to correctly calculating the posterior probability of SB conditional on SA, and then apply a proper scoring rule with the realization outcome to be the reported SB. And that enforces the incentive. So this is the knowledge about distribution. And the community really doesn't like that, of thinking that, okay, it's too much to assume that the principal knows the distribution queue. We really want a setting, elicitation setting, such that it doesn't require the principal know the distribution queue, because thinking that the principal knows how the signals and the underlying event X are correlated is just too much to ask. So that's the next stage of the progression of the elicitation mechanism, is that the principal doesn't know the distribution. The principal also doesn't know the realization. So we're still in the without ground truth setting. In this case, we can have multiple agents, but a single task is no longer sufficient. So here we actually need multiple tasks. For this example, let's just think about that. We have two agents, Alice and Bob, and we have two tasks. And we can assign Alice and Bob to complete either one or both tasks. In this case, if I want to provide the right incentive for Alice, I actually need to assign both Alice and Bob to complete one task, task one here, and I need to assign Bob to complete the second task. And the usual assumption in this setting is that the tasks are IID distributed. So essentially the tasks are a priori similar. And the agent signal, so they jointly follow some fixed distribution, but across all the tasks, they're also IID distributed. So it seems that we're not really making any requirement for the principal to know any knowledge about the distributions. But the IID assumptions essentially are characterizing a setting where the principal does have some knowledge about the underlying information structure. And the correlated agreement mechanism would apply the following payment rule to the agent Alice here. So it is essentially rewarding agreement between Alice and Bob's report for the first task, which is the task that they both work on, and will penalize the agreement between Alice and Bob for Alice's report of the first task and Bob's report for the second task, because over agreement on different tasks shouldn't happen statistically. So this is a simple bonus penalty payment. And with this type of payment, this can ensure that truthful reporting is a Bayesian-Nash equilibrium. So it actually achieves more than that. It also ensures that this truthful reporting equilibrium receives the highest payoff for each agent. So people call it like either strongly truthful or informed truthful, depending on the comparison. Okay. And there are many other more like sophisticated mechanisms that has even stronger property. So for example, the deterministic, the DMI mechanism that Yiling has, the deterministic mutual information mechanism that Yiling has invented, is also a multitask setting. They have achieved the strongest possible incentive guarantee, which is dominant strategy truthfulness for this setting, which is amazing. But I want to emphasize that it also leverages on the IID tasks, IID joint signal cross-task assumption. So essentially, the principal still has some knowledge to use in order to design the incentive. So if you agree with me, it's only possible to guarantee truthfulness if the principal has some knowledge to leverage. And if it reach to this conclusion, it makes us tempted to think about, do we really need to limit our success to the IID task setting? Because the multitask setting has the most success so far, but it does require that the agents are working on the tasks that are priorly similar. So that leads to what I want to talk about, which is what I call the context-aware elicitation. Essentially, we can think about that if we have rich elicitation tasks, which clearly violates the IID task assumption, is there any knowledge that we can leverage about the structure of our elicitation task such that we can still achieve truthful elicitation? And by thinking this way, it allows us to move away from IID setting and consider elicitation for two settings. So the first setting is to elicit pairwise comparison information. So for example, if we're thinking about Van Gogh's paintings, if we really want to get a complete ranking of Van Gogh's painting, it's probably very easy to get a ranking for the most famous ones. But Van Gogh was very, very productive. So he had more than 900 paintings just between the years of age 27 and 37. So 10 years has more than 900 paintings. So about like one painting for 3 or 4 days. Very productive. So if we want to get a complete ranking of those 900 paintings, it would be very difficult to elicit the information for complete ranking from any individual. And people tend to try to get partial information, asking individuals to give pairwise comparison information. And pairwise comparison for items that's coming from underlying consistent ranking, they're not independent tasks. So they're clearly correlated, not independent tasks. So we can't just take the existing mechanism and apply to this setting. But we want to think about whether it's possible for us to still achieve truthful elicitation in this setting. And the second setting is if we want to elicit opinions over social networks, let's say binary opinions, because of homophily, we know that individuals' opinions are correlated. So I'm more likely to share the same opinion with my friends than with people that I don't know. Okay? And we also are interested in simple mechanisms. So in order for us to think about it, we start with the really simple bonus penalty payment function that you've already seen in the multitask setting early on. So let me give a generic version of a bonus penalty payment function just for 3 pieces of binary informations. So think about that. We have 3 agents. Agent I, J, and K, they each have a random piece of binary information. So the uppercase SI, SJ, and SK are random variables. And they can take values of -1 or 1 because it's binary. And they may choose to report something different. So we use the SI hat, SJ hat, and SK hat to represent their report. And the bonus penalty payment is a function. And this function is used to reward the first agent, the agent I, according to his report SI hat, and also the report of 2 other agents, SJ hat and SK hat. And it's a very simple function. It basically just to say that I'm going to calculate whether SI hat and SJ hat are the same. So reward the agreement. So if it's the same, okay, great. So if it's the same, this term will be 1. And then, so this is the bonus part. And then the penalty part is saying that I don't think I and K should agree. So if they actually agree, this is going to be a penalty. So I will subtract the agreement between I and K. And the scalar doesn't matter.
This is for same task, 3 different agents?
So I'm not even introducing task because I want to first introduce this function that takes into the 3 report. And when the agent has 3 pieces of information. And I want to try to understand, so under what conditions this function actually will incentivize the agent to report truthfully. So try to understand like how powerful this simple function can be and what are the settings this simple function can work. So here there's not even tasks. Okay. So this is essentially it's just the function that we have seen before with correlated agreement. But now I don't have the label of tasks. I just have very generic information. Okay? And this is the payment for agent I want to emphasize that. So we want to use this function as a payment function for the first agent. Okay. So we ask the question, when does the bonus penalty payment rule actually can guarantee truthfulness? That has a very interesting characterization. It's a condition that we call the uniform dominance. And let me introduce the mathematical definitions and explain what it means. I think it should be very intuitive. So what does it mean is that if we consider the 3 agent signal, so there are random variables, SI, SJ, and SK, they have some joint distribution P, so generic joint distribution P. We say that SJ, the signal of the second agent, uniformly dominates SK, the signal of the third agent, for SI, the signal of the first agent, if regardless of the realization of SI. So whether SI's realized signal is +1 or -1, from SI's perspective, the probability for Sj to have the same signal as Si is always higher than the probability for Sk to have the same realization as Si. So uniform is uniform across the realization of Si. And dominance really just means that, oh, Sj is going to agree with Si more from Si's perspective than Sk. So if this is true, we call the tuple, which is the order tuple. So we write Si, Sj, and Sk, meaning that from Si's perspective, Sj uniformly dominates Sk. So we call it a uniformly dominant tuple. So if I have 3 pieces of information that satisfies the uniform dominance condition that I just introduced, so which is intuitively just saying that agent I knows that agent J are more likely to agree with agent I than agent K does. So that's what this definition means. Then the bonus penalty payment function actually guarantees a certain level of truthfulness. So what does it mean? So it means that suppose both Sj and Sk are going to report truthfully, then it's always the best action for Si to also report truthfully when Si, Sj, and Sk is a uniformly dominant tuple.
Excuse me, just two big question. So basically, this condition says that I is more correlated with J than I is correlated with K, right? That's your condition.
Yes.
So this guarantees that I will be truthful. Does it also guarantee J will be truthful?
So far it's not. If I'm just looking at the payment function for I.
Right.
So if I'm just looking at the payment function for I, what this guarantees is that if both J and K are truthful, then I also want to be
corresponding
truthful.
function for agent J as well, the guy in the middle. You have
Uh,
a corresponding payoff function for J as well.
Right. So the ideal case, I guess you probably already guessed, if I want to design a mechanism that induces truthful reporting as equilibrium, I have to have such a payment rule for every agent.
Right. I think it's pretty obvious to know what K's payoff function should be, given what I's payoff function should be, because these are the two whatever extreme guys. But the guy in the middle, I think that's more subtle, right?
Right. So basically, what I need to do is that I need to find a uniformly dominant tuple for every agent. So if I can achieve that, so they could have different pairs. So in order to calculate a payment for agent I could pick agent J and K. But in order to calculate a payment for agent J, I could pick other agents. So they don't have to be I and K.
I see. So you may require more than 3 guys or whatever.
Yeah, exactly. So essentially, but this gives the structure of thinking about if we do have a uniformly dominant tuple, then just using the bonus penalty payment function to reward the first agent will give the agents the incentive to report truthfully if the other 2 agents are also report truthfully. Okay. So what's interesting is that the bonus payment penalty function, in some sense, is also unique. So what do I mean? Is that if we want a payment function that strictly induces truth telling for all uniformly dominant tuples, then such a payment function can only be an affine transformation of a bonus penalty payment. Essentially, a positive affine transformation. So in that sense, just focusing on the bonus penalty payment function will allow us to analyze the set of the equilibrium. Okay. So So I think what seems to be suggesting is that we have a very simple payment function, bonus penalty payment function, very simple. If we're having an elicitation task, it could be a complicated elicitation task. One way it's possible for us to achieve truthful elicitation is to, for each agent I, find two other agents J and K, such that agent J's information uniformly dominates agent K's information for agent I. And then we just use the BPP to pay agent I. Since we're doing this for every agent, this just induces truthful reporting as an equilibrium. So that's the hope. But the question is, can we achieve that? So let's take a look at the pairwise comparison information structure. So when we're thinking about individuals have private information about pairwise comparison of items, it's usually this information has a lot of structure. So we try to model this structure, capture the structure using the Bayesian strong stochastic transitivity model. And this actually is not restrictive because it includes most of the parametric ranking models as special cases. So this is quite general, trying to capture the relationship of pairwise comparison information. So let me explain this. So the setup is that there is a set of items, and these items can have some unknown state, theta. And this theta could be the strength vector of the candidates. So if you're thinking about multiple items or multiple candidates, they have their innate strength quantity. And then that will be this vector theta. And this vector theta could be drawn from some prior distribution. And then we don't know the realization, but any realized theta will induce a stochastic comparison function. Basically, this comparison function, when given a pair of items, A and A prime, will report an outcome. So it will report value 1 when A is preferred over A prime, and it will report value -1 when A prime is preferred over A. So, and the probability of the comparison function for the opposite direction pairs must sum to 1. Okay. And when asked to compare a pair of items A and A prime, so an agent receives some private information, which is just a random draw according to this stochastic comparison function. So it's a random variable, it's a binary random variable. And I think the key property of the pairwise comparison information structure is what we call the strong stochastic transitivity. But let me try to explain this. So without any uncertainty, we all know what transitivity means. So it means that if I prefer A over A prime, and I prefer A prime over A double prime, then I prefer A over A double prime. But because we're talking about private informations, there's uncertainty. So the comparison function, only with certain probability, are going to return that I prefer A over A prime. So the strong stochastic transitivity basically says that if for a given comparison function, the probability that this comparison function are going to say that A is preferred over A prime is greater than 1/2, if that's the case. And also the probability for the comparison function to say that A prime is preferred over A double prime is greater than 1/2. So basically saying that the comparison function thinks it's more likely that A is going to be preferred over A prime. And it's also more likely that A prime is going to be preferred by A double prime. Then the transitivity in this case is that the comparison function must say that the probability that A is preferred over A double prime will have a higher probability than either of the two probability above. So it's just more likely for A to be preferred over A double prime. So that's the transitivity in the stochastic setting. Okay. So we also can think about, since we don't know theta, so a priori the items are similar, but after the realization of the theta, the items are distinct. Okay? While this may appear to be abstract model, so I want to emphasize that the models that you're probably very familiar with for rankings, the Thurstone model, the Bradley-Terry-Luce model, the Mallows model, and also the more general randomized utility model, all are special cases of this level. They all satisfy the strong stochastic transitivity. So in some sense, if we think that it's a reasonable way of thinking that pairwise comparison information are coming from a model like this, so we could have a specific parametric model like the Thurstone model, or we just think that, oh, since all these models satisfy the SST property, that's the key property we are going to be working with. Okay. Then the individual's private information about the pairwise comparison outcomes really have some structure that we can leverage on. And in particular, it allows us to identify uniform dominance in pairwise comparison. So SST model immediately implies that for any three distinct items, A prime, and A double prime, if we assign the pairwise comparison of A prime to agent I, so agent I's information Si is the random variable of the pairwise comparison between the pair A and A prime, then we can choose agent J and assign the pairwise comparison between A double prime and A prime, and choose agent K and assign the pairwise comparison between A double prime and A. And then these three pieces of information is a uniformly dominant tuple. And let me try to just spend a little bit more time here.
Sorry, did you mean to change the order?
I do mean to change the order, because the way to think about it is that, so suppose agent I thinks that A is more preferable compared with A prime, then it is true that for any other item, A double prime, from agent I's perspective, he thinks that the probability that A double prime is going to be preferred over A prime is going to be higher compared with A double prime is going to be preferred over A. Because if A is my favorite, I cannot believe that it's impossible for any other item like to be more preferable to me compared with A. So this is essentially capturing that. So the SST model essentially gives such a structure of uniform dominance. So this allows us to think about, for pairwise comparisons, how we can assign the pairs to individual agents such that we can correctly find the pairs where we can apply the BPP payment function. So this is essentially saying that if we properly chosen the pairs, according to, if I assign the comparison between A and A prime to agent I, then I need to find two other agents. One, I will assign the comparison between A double prime and A prime, and the other, I will assign the comparison between A double prime and A. And then apply the BPP payment function to agent I. So this induces truthful reporting as a Bayesian-Nash equilibrium, and it's actually have a slightly stronger guarantee. So we call the symmetrically strongly truthful, because it also has the highest payment for every agent compared with any other symmetric strategy equilibrium.
Excuse me. Maybe I'm just not very familiar with the literature. Can you just go back one slide? So what is this model? So basically there are 3 items and there's an objective comparison between this A prime, and A double prime, but I just don't know this, right? Is that the setting?
Yeah, so you can have any number of items.
Maybe you can understand 3. Okay,
Right,
3
so let's just say there are 3.
Ranking over these things.
Yes.
You guys know this, I don't know this. I'm trying to figure it out, right?
Right.
And you are saying that the way in which you can figure it out, use your payoff, is to use your whatever, your transfer function, and then you are saying you let agent I report whether A is better than A prime, let agent J report whether A double prime is better than A prime, right? Is that?
Yeah. So notice that the agent's private information is a noisy version of the underlying true ranking. So usually the type of model, the ranking model will assume that there's an underlying true ranking. And then the agent's observation of a pairwise comparison, which is the agent signal, is a noisy version of that. So with some probability, it could flip the true ranking.
Okay, so you allow the agent, okay, because if everyone perfectly knows the ranking, if there's objective ranking, everyone perfectly knows the ranking, then an easier way would be just to ask Jason, hey, what is your willingness to pay for A, what is your willingness to pay for A prime, what is your willingness to pay for A double prime, and then just let him say something, and then based on some probability, it just counts, and I just pay him the money in exchange for an item, and then you can. There are easier ways of soliciting whatever a complete and transitive preference, right? I don't know why do you have to do this, but yeah, given that Jason doesn't have complete information, maybe there's a reason to use this more complicated thing. But okay,
because private information usually involves uncertainty, so there's so we don't have the complete information. Okay, so I think I have 3 minutes. Do I have 3 minutes, or should I stop?
Maybe let's stop at 9:20.
Oh, 9:20. Okay, I have a few more minutes. I think I can finish. So then I think the idea is very natural that we can apply a very similar idea to networked data, because sociologists have all observed that people's opinion over social networks has homophily. So which basically is saying that so I'm more likely to have similar opinion with my friends, with people that I know, compared with people that I do not know. And a mathematical model that's trying to capture the homophily is the EC model. The EC model is essentially think about the agents are the nodes of a graph, and the edges between 2 nodes, basically saying that these 2 agents are friends. And if every node, every agent has some binary opinion, then the EC model will generate the opinion according to an energy function that relates to a vector that's, the vector is called the beta vector here, where each element beta ij for every edge captures the correlation of the opinions between node I and node j, or agent I and agent j. So I think the details are not important. It's basically a model that has been proposed a long time ago that's trying to capture the correlation of opinions of people over a social network. And for this setting, it's very natural to think that we can also use the BPP payment function in the following way. So for each agent I, we just choose a friend as agent J. And then we choose a non-friend as agent K. And then we again have a uniform dominance pair, a tuple, uniform dominance tuple, and we use the BPP function to pay agent I. So if we choose the pairs carefully, we would expect that we can have good elicitation. And in fact, that we're able to prove that the BPP payment will admit a symmetrically strongly truthful Bayesian-Nash equilibrium for eliciting network data if the network is generated using the EC model and has bounded degree and a large enough correlation parameter. So we're able to get some theoretical guarantee if the correlation is high. Okay. So let me finish by showing some experimental results, which can be viewed as the stress test of what we have proposed for the BPP payment mechanisms. So for pairwise comparison, we use the sushi preference data set. So which is a data set that people gives rankings, preference rankings of 10 sushi flavors, 10 different type of sushi. And what we tried is that we take those data set as people's true preference. And then we apply our BPP payment function on the true preferences and take that as what the truthful reporting would receive under the BPP mechanism. And then we compare that with if all the agents just report uniformly randomly, taking an informative strategy and calculate their payment under BPP. So that's the orange curve here is the uniformly random uninformative strategy payment, and the blue one is the truthful one. And what's being plotted here is the empirical CDF. So essentially, a point on the curve is showing what's the percentage of the agents receives a payment that less than the corresponding value here. And as you can see that the orange curve is consistently on top of the blue curve, basically saying that there are more agents receives the higher payment when they report truthfully under the BPP mechanism. So the figure on the right is comparing truthful reporting under BPP with an agent unilaterally deviating. So when other peer agents are reporting truthfully, but the single agent is deviating from truthful reporting. And as you can see that, we still observe that they receive less payment compared with the truthful reporting. And for the network data setting, so we use the data set last.fm, so which are kind of a music listening platform. And what I'm showing here is the figure for Lady Gaga, so the music for Lady Gaga. And it's the same, the left is comparing truth telling with uninformed, and the right is comparing truth telling with unilateral deviation. And the same trend is observed that the blue curve is always below, indicating that truth telling returns higher payoff in general. So let me just close here. So I think the hope is that, so eliciting information is incredibly hard. So we really have to leverage on some knowledge. But if we accept that we have to leverage on some knowledge, so that opens up the possibility of thinking what are available knowledge that we have for a specific elicitation setting, and how we can leverage that knowledge to make simple mechanism work for truthful elicitation. So thank you very much. That's so.